Wow. Well, at least you all are here. It's like, where is everybody today? Okay, let me get these lights on. We're gonna remind ourselves of what we were doing. We're looking for the condition under which convection is going to occur in a star. And so we had this bubble that we were saying, well, what if it rises for some reason, just starts to rise? What will make it keep on rising? And so we want to talk about what those conditions are. So, right, we had this idea of here's this bubble. It makes a little increment in radius. It rises up a little bit. It gets a little bigger because it's going to expand and do work on its surroundings. And so we need to compare conditions in the bubble to conditions in the surroundings. And we said that the bubble is going to rise adiabatically. In other words, fast enough that there's just no time for any heat flow into or out of it. Bubble rises adiabatically. No heat flow in or out. So its temperature change is entirely due to the work it does on its surroundings. Work it does on the surrounding gas, plasma, whatever you want to call it. It's really plasma in a star. There's ionization that has happened. And so the idea is that there's going to be some rho final of the bubble, right? And there's going to be some rho final of the surroundings outside. It's going to rise, its density is going to change. Initially, its density is essentially the same as that of the surroundings. Maybe some fluctuation caused it to be slightly less, but essentially starts out where they're same density. It rises and expands, and the question is, does it become more or less dense than its surroundings? And so if the final density of the bubble is less than the final density of the surroundings, the bubble will be buoyant and continue to rise. And this will be the condition that convection would be favored. A rising bubble keeps on rising. Flip it around, a sinking bubble keeps on sinking. So now I have to ask, do y'all know how buoyancy works? Is that something that you've learned before? Is there anybody, and don't be shy, who has not learned how buoyancy works before? I don't know, does that cover it all in like physics 110, 111? Is that talked about at all?
You mentioned like very small.
Uh-huh. Okay, yeah. So, I mean, just as a refresher, right? So you probably know the condition for something to be buoyant is it's less dense than whatever it is surrounded by, right? You all know the story of Archimedes, right, in the bathtub. Eureka! He runs out of the bathtub because he's figured out what makes things float or not float, right? So just as maybe it's a refresher, maybe you don't know this, if I have something that is inside water or anything else for that matter, it could be a balloon surrounded by air or whatnot, then we know that if it is, well, so first of all, if this was just water, so let's say all this is water. It doesn't have to be water, it could be anything. Water, and here is, inside it's still more water, right? It's just some of the water that's surrounded by other water. Well, then what are the forces on this parcel of water? I've drawn this arbitrary surface to represent this parcel of water. And if the water is undisturbed, that parcel of water is not rising or sinking. What are the forces on it?
Gravity.
Gravity, yeah, gravity. And what else? If that were the only force on it, it would start sinking, right? Pressure, right? Yes, there's forces on the blob of water are gravity, and that'll be its total weight, mg, right? And that is downwards, and pressure exerted on it by the surrounding water what way does that force point? What way does the pressure force point? Is the bubble sinking? Is the bubble rising? Or a blob, it's just a blob of water. Is that blob of water, we call it a bubble because we were kind of doing that over there too, but it's a blob because it's not really a bubble. it's water here, okay? Is it sinking or is it rising at this point? It's just more water in there, so it's not sinking or rising. So what has to be true about the pressure force and the gravity force on it? Those are the only two forces on it, so what has to be true about them? They're equal and opposite, right? There's no net force, so the pressure force, right, not rising or sinking, so net pressure, external pressure force, because it can only be applied on it by the surrounding water, the net external pressure force is equal and opposite. Equal and opposite. So therefore, pointing upwards to the weight of the blob, right? Well, how's that come about? What must be true about the pressure in order for it to produce a net upwards force on it? What has to be true about the pressure in there, in the water? If the pressure in the water was the same everywhere, would there be a net pressure force on that? No, there wouldn't, right? So what has to be true about the pressure lower down compared to the pressure higher up? Yeah, the pressure has to increase as you go down so that there's a larger force upward on the underside of the blob than there is a pressure force downwards on the top of the blob, the upper surface of the blob. And it's going to have to be true that the net pressure force has to be equal and opposite to the weight of that thing. Right? So that's fundamentally what happens if there's just water there. The idea with buoyancy, the argument is replace the blob of water with some object. Made of another material. Maybe even it's just a bubble of air, but it could be a thing of wood or a thing of concrete or iron or whatever, an object made of another material. Does this change the net pressure force on the blob? Will that change the net pressure force on the blob? Yes or no? It will not. Why not?
The blob can't exert a force on itself. That's going to replace it
But I'm asked, but the pressure force comes from the surrounding water, or air, or whatever it is we're talking about here. So it's the surrounding water we need to worry about here. Does the water care what it's pushing on? No, the water doesn't care what it's pushing on. So the answer is no. The surrounding water doesn't care what it's pushing on. So the pressure force is the same as it was before. So what can you say about the pressure force on now this object? We've turned this into an object, right? I'm cheating, I get to just erase that, but you know, now there's an object there. It's not made of water anymore. The pressure force is the same as it was before. What was it before? It was equal to the what before? I'm not asking for a number, I'm asking for a conceptual answer here. Yeah, so in particular, it was equal to the gravitational force on that water. What do we call the gravitational force on that water? What do you call the gravitational force on you? That's your weight, right? So the pressure force is equal to the weight of the water that was displaced by the object. That's the crucial point. That you've displaced a certain volume of water, that doesn't change the pressure force because the water doesn't care what it's pushing on. And so the upwards pressure force is equal to the weight of the water that the object displaced. Does that make sense? You've moved some water out of the way, the pressure force doesn't change because the water doesn't care what it's pushing on, so the upwards pressure force is equal to the weight of the water displaced. Is still, it was before too. Before the water was displaced, it was equal to the pressure, it was equal to the weight of that water. The upwards pressure force is still equal to the weight of the water displaced. Of the water displaced, moved out of the way by the object. So when will the object float versus when will it be buoyant versus when will it sink? What would make it sink?
If its weight was stronger.
If its weight is more than the weight of the water displaced, right? Because the downward force on it is the weight of the object itself. The downwards gravitational force on the object is the weight of the object itself. So there will be a net downwards force. The object will sink if it weighs more than the water that it displaced. You've probably heard that before. Nobody should graduate from college, especially if you're a physics or an astrophysics major, without knowing this concept. And I don't know if you knew it before or not, but if you didn't, here it is, okay? So object sinks if its weight is greater than the weight of an equal volume of water, right? Because that's how much water it's displaced. An equal volume of water. We could say of the water it displaced, but more kind of relevantly, if its weight is greater than the weight of an equal volume of water, and of course it'll float, it's buoyant, if it's the vice versa. Object will be buoyant. I think this is right. Buoyant if it weighs less than an equal volume of water. Okay, what's that imply about the density for it to be buoyant? How does its density have to compare to the density of water for it to be buoyant?
It's even more dense than the water.
Let's see, if it's more dense than the water,
Sorry, less dense.
yeah, less dense than the water, right? If it's less dense than the water, well, the weight is the density times the volume, right? So if its density times that volume is less than water's density times that volume, that's the same thing as saying that its mass is less than the water that it displaced, that its mass is less than an equal volume of water. And if it's a composite object, you'd be talking about its average density as opposed to it's just the density, but the concept is the same. In other words, ta-da! If the bubble's final density is less than the final density of the surrounding gas, then it'll be buoyant and keep on rising. That's the gist of this argument there. Makes sense? What questions do you have? So go forth and tell your friends why things float and sink. When I was a kid, sank in a life jacket, thereby proving that I'm just totally dense or something like that. Right? Why does taking a breath help you float? Because you're not changing your weight, but you're increasing your volume and therefore decreasing your average density. Humans are just about the same density on average as water, and so we're kind of on the borderline there. And so if you take a deep breath and increase your volume a bit, then that will help you be buoyant because you'll have the same mass, but you'll have occupied more volume. Your average density will become smaller, and so you've got a better chance of floating. Yes?
What about if it's like really salty water? Why does it work that way?
Because salty water is more dense than water without salt in it, because the addition of the sodium chloride makes the water more dense, and therefore you have to have a denser object in order to sink in it. So that's why, that's why, what is it, like in the Great Salt Lake, or especially like, I guess it's the Dead Sea, it's very easy to float because of the fact that the water's denser. Yep. Okay, what other questions do you have? So this is our condition. Can I erase this, or is somebody still writing? Are you still writing? Yeah, can this go? Kill, kill, die, die, okay? All right, so we want the density to be smaller. Can we infer something about the temperature based on this? According to the ideal gas law, we have that the pressure, and the way that astronomers like to write it generally is, we don't typically do the Pivnert thing where we do the number of moles times the gas constant, although we're actually going to start doing that some. But usually in physics or in astrophysics, and often in physics as well, we like this version of the ideal gas law. Remember this? So that's the Boltzmann constant times the temperature. And what does N represent? The what?
Number density?
Yeah, it's the number density, right? N is the number density. Or in other words, the number of particles per cubic meter. And it doesn't matter what kind of particles they are in the ideal gas law. They could be electrons, they could be protons, they could be hydrogen atoms. It's just the total number of particles per cubic meter. And this is equal to the mass density times the Boltzmann constant times the temperature divided by the mean molecular weight. This isn't the reduced mass. The mean molecular weight times the mass of a hydrogen atom. So I'm introducing the concept of mean molecular weight, which we're going to pound into the ground. This is something that's a very commonly used concept here. So m sub h is the mass of a hydrogen atom. Mass of an H atom, and mu equals m bar over mh is the mean molecular weight, mean as in average, mean molecular weight and m bar is the average mass per particle. So this, in other words, is just a rewriting. The claim here is that the number density is rho over mu mh, rho over mu mh, because by the definition of the mean molecular weight, mu mh is m bar. So it's rho over m bar. It's the mass density over the average mass per particle. So what's the units of mass density? SI? What are the SI units of mass density? What's the SI unit of mass? Kilogram, right? Kilogram. So, and then what density is what? Density is what per what? What is density? Mass per unit volume, right? So SI density units are kilograms per? Whoops, 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 whoops. Meters cubed, right? Volume is meters cubed.
I think I'm picturing it wrong in my head.
Yeah. It's just meters cubed. So fundamentally, it's kilograms per cubic meter, right? So this is kilograms per cubic meter, right? Divided by the mass, average mass per particle. So in other words, this is average number of kilograms per particle, right? So what does this work out to be? If I take in every cubic meter the number of kilograms times the mass per particle, divide kilograms by kilograms per particle, what's that turn into? What is kilograms divided by kilograms per particle? Put another way, okay, if I told you the total mass of people in this room, in some room, was, I don't know, 2,532 kilograms. How could you turn that into the number of people in the room? What would you need to know to turn the total mass of the people in the room into how many people were in that room? What would you need to know? The average mass of each person, right? If you took the total mass and divided it by the average mass of each person, that would be the total number of people in the room. If you have a bunch of particles, atoms, electrons, whatever, in a box, in some cubic meter, and you know the total mass in that cubic meter, that's the density, right? Because that's kilograms per cubic meter. If you divide that by the average mass per particle, It's just like the people example. That'll give you the total number of particles in that cubic meter, right? So kilograms over kilograms per particle, the kilograms cancel, and 1 over particles is particles, right? Because it's 1 over particle, so that's particles unit-wise. Particles per cubic meter. Why? What do we call the number of particles per cubic meter? What's the number of particles per cubic meter? What do we call that? That's the number density, right? That is, why, what symbol do we use for number density? N, yes, right, N. So in other words, yeah, N is rho over mu mh because it's rho over the average mass per particle. It's the number of kilograms in every cubic meter divided by the average number of kilograms per each particle. That's the number of particles in every cubic meter. And we will often use this expression as the ideal gas law, rho kT over mu mh. It's a very useful way to write the ideal gas law. Let's do a couple of examples of rough calculations of mu for different situations. What is mu, the mean molecular weight? Sorry, there's not enough symbols to go around. This is not the reduced mass. It's the mean molecular weight. What is mu for pure atomic neutral hydrogen? What would mu be for pure atomic neutral hydrogen? What is the average mass per particle in terms of the mass of a hydrogen atom, right? Because mu is equal to m bar over the mass of a hydrogen atom. If I've got nothing but hydrogen atoms, what is the average mass of a particle in terms of the mass of a hydrogen atom? It's the mass of a hydrogen atom, right? In this case, if everything's a hydrogen atom, then m bar is mh, and we're going to divide that by mh, right? The average mass per particle is mh because it's frickin' hydrogen atoms. So what is mu in this case? 1. So mu is 1 for pure atomic neutral hydrogen. What is it for fully ionized hydrogen? So I'm just going to get a rough calculation here. You could do this more precisely, but it's good to be able to just do back of the envelope quickie calculation. So for each H atom, well, I put it this way. Each H atom contributes how many particles? How many particles does each H atom contribute if they're all ionized? Each H atom contributes a what and a what? If I ionize it, each H atom is responsible for what two things? If it's just ordinary, not deuterium hydrogen, just ordinary hydrogen, if I split apart an H atom, what do I got? A proton and an electron, right? Each atom contributes a proton and an electron. So for every 2 typical particles, one's a proton, one's an electron. What's the mass of a proton in terms of the mass of a hydrogen atom? Approximately, because I'm just doing a quickie calculation here. What's the mass of a proton in terms of the mass of a hydrogen atom?
Mass of the hydrogen atom.
Yeah, it's basically the mass of a hydrogen atom. The mass of a proton is almost the mass of a hydrogen atom, because all it's doing is, it's okay, it doesn't have the electron, but whatever, that's okay. And what is the mass of an electron? kind of to the same level of approximation for doing this quickie calculation?
0.
0, yes, 0, because it's just a little more than 1/2000th the mass of the proton, right? So to a good approximation, we've got now twice as many particles as before, and half of them have the mass of a hydrogen atom and half of them are massless. To this approximation, right? So mu is equal to approximately the mass of a hydrogen atom plus 0 it's really, it's really the mass of a proton plus the mass of an electron divided by the mass of a hydrogen atom. That's not exactly equal to the mass of a hydrogen atom, by the way. Why isn't a hydrogen atom's mass equal to the mass of a proton plus the mass of an electron? Because it's not. If it's in the ground state, how much less is the mass of the hydrogen atom than the mass of a proton plus the mass of an electron? Think relativity. Think relativity. Mass and energy have equivalence to one another. If I put an electron in the ground state of hydrogen, how much energy is given up to do that? There's binding energy. How much?
13.6.
Yeah, that's 13.6 electron volts. That is a reduction in the mass of the hydrogen atom compared to the sum of the masses of the proton and the electron. A hydrogen atom's mass in terms of electron volts is 13.6 electron volts less. If you want to put it in conventional units, 13.6 electron volts over c squared, but in units where c is 1, 13.6 electron volts less than the mass of a proton plus the mass of an electron. The mass of a proton is about 938 giga-electron volts, and the mass of an electron is about 511,000 electron volts, a little more than 1/2000th the mass of the proton. So these are not equal to one another. You should be aware of that. And if you promote if the atom absorbs, so maybe you never thought about this before, if that atom in the ground state absorbs a proton and jumps up to n equals 2, you have thereby increased the mass of that atom by that 10.2, it is, I think, electron volts of that transition. A hydrogen atom in n equals 2 literally has more mass than one in n equals 1 because you've reduced that binding energy. That photon got absorbed. That energy has increased the mass of that hydrogen atom. It has more mass as a result of that. Einstein wasn't kidding when he said that mass and energy have equivalence to one another. So that's for real. So it really does change the mass. But back to our story, this then is essentially the mass of a hydrogen atom plus nothing over the mass of a hydrogen atom, making an approximation here. And so, wait, got to be careful. So got to be careful. The average, let me think here. I'm looking for the average mass per particle here. So what is the average mass of a proton and an electron? There's two of them, right? So I shouldn't have written that. It's m bar over mh. And m bar here is going to be, it's really 1/2 times the mass of a proton plus the mass of an electron. But that's approximately 1/2 the mass of a hydrogen atom plus 0, right? To this approximation, I'm trying to find the average mass of a proton and an electron. The proton has the mass of a hydrogen atom to a good approximation. The electron is essentially 0 mass. So what is the average mass per particle for ionized hydrogen? Okay, I feel like people are staring at me like this isn't making sense, you're not following. And it's not hard, so be sure you wrap your head around this. Two particles, one's got the mass of a hydrogen atom, one is massless, right? So what's their average mass? Put another way, what is the average mass, compared to my mass, what's the average mass of me and that chalk holder, to a good approximation? No, that's not the average mass. That's the total mass.
1/2 you.
Half of me, because there's two particles here, right? There's me and this. There's two objects here. So the average mass is the total mass divided by 2, because there's me plus this. So if I grab something that's essentially almost massless, the average mass of us two things is basically half of my mass, because now there's two things that I'm averaging together. If I ionize the hydrogen, you got protons, you got electrons, and so the average mass per particle now is half the mass of a hydrogen atom, because you have every 2 particles is a hydrogen atom plus nothing, to a good approximation. So m bar is essentially half the mass of a hydrogen atom, and so therefore the mean molecular weight, the average mass per particle in terms of the mass of a hydrogen atom, what's the mean molecular weight for pure ionized hydrogen? 1/2, yeah, 1/2. It's essentially 1/2 or 0.5. Is it exactly that? No, we would actually have to put in the actual numbers. That's not totally massless. That's not exactly equal to the mass of a hydrogen atom, blah, blah, blah. But it's awfully close to the mass of half the mass of a hydrogen atom. 2 more examples to be sure you're getting this. Pure neutral helium. For pure neutral helium, and it's the ordinary helium that has 2 protons and 2 neutrons in the nucleus, what's m bar, the average mass per particle, if all the particles are neutral helium atoms? Helium. It's meant to say helium here. What's the average mass per particle? To an awfully good approximation if the particles are all helium atoms.
2 with P.
Nope, not 2. Because it's 2 protons and 2 neutrons. How do neutron masses compare to proton masses?
Half in P.
No. A neutron's actually a little more massive than a proton is. It's slightly more massive than a proton, but just slightly. The mass of a neutron and the mass of... Yeah, not a lot. Yeah. So it's approximately the mass of... Well, it's approximately 2mp plus 2me plus 2mn plus 2me. And I say approximately because if it's an atom, there's binding energy, and so it's a little bit less than the mass of the particles separated from one another. We say, we ain't counting electrons when you got protons and neutrons around. And what's the mass of a proton in terms of the mass of a hydrogen atom? We've already said it. It's essentially mass of a hydrogen atom. How about the mass of a neutron in terms of a mass of a hydrogen atom? Mass of a hydrogen atom, because protons, neutrons, they're all about the same mass, and that's all about the same as the mass of a hydrogen atom. So in other words, m bar is, to a good approximation, 4mh here. Sorry, the mass per, yeah, m bar, yeah, the mass per particle, yeah.
What do you have to divide it by 6?
This is no, so far we're finding out what m bar is, and we don't have to do that because the helium atom is 1 particle for these purposes. If it's the ideal gas law, if it's acting as a single particle, and they are, then the mass per particle here, for the purposes of the ideal gas law, if you've got helium atoms, they are intact units. They are the things that are bumping off of one another, creating the gas pressure. So m bar is 4 times the mass of a hydrogen atom. It's the mass of a helium nucleus, which is about 4 times the mass of a hydrogen atom. And so what's mu in this case? Mu is m bar over mh, right? It's the average mass per particle expressed in terms of the mass of a hydrogen atom, or divided by really the mass of a hydrogen atom. So what's mu in this case? 4. 4. Notice that mu is a dimensionless number. It's 4 in this case. Not exactly. We would really have to account for the binding energy and the fact that a hydrogen atom's mass also has binding energy, blah, 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 but it's awfully close to 4 in this situation. What about, what's the next one I'm going to do? I did pure neutral hydrogen, I did pure ionized hydrogen, I did pure neutral helium. What am I going to do next? What's the pattern?
Pure ionized helium.
Pure ionized helium, yeah, pure ionized helium. Pure, fully ionized, right? We strip both electrons off. Fully ionized helium, okay? So now, each helium atom contributes what to the mix? If I ionize it, there's more particles than there were before, because before a particle was a helium atom. Now each helium atom has turned into what particles after I fully ionize it? I got myself a... Yeah, I've got 2 electrons and a helium nucleus, a bare helium nucleus, right? Each helium atom contributes a helium nucleus and 2 electrons. 2 electrons. What's the mass of that helium nucleus in terms of the mass of a hydrogen atom? 4, again, right? It's approximately 4 times the mass of a hydrogen atom because it's 2 protons, 2 neutrons, and each one's about the mass of a hydrogen atom. And what's the mass of those 2 electrons to the level of approximation we're making here? Yeah, 0. We're not counting them. So now, count them. 3, 1, 2, 3. 3 particles have mass 4 mH. So the average mass per particle is 4 mH over 3, right? Because each helium is giving you 3 particles, and so the average mass per particle will be the mass of that helium, 4 mH, divided by 3 particles now. So what's mu in this case? 4/3. Mu is 4/3 for pure ionized helium. Why do we care about this? Well, we're going to care about it plenty in the future too, but right now we're caring about it because we're going to see that if you've got a rising bubble and you're in a region that's at a transition temperature for ionization, so like if you're in the hydrogen partial ionization zone, in other words, the depth within the star where the temperature is 10,000 Kelvin plus or minus 1,500 Kelvin or so, where hydrogen is going from neutral at lower than that to ionized at higher than that. As our bubble rises, it will be cooling down, and if it starts out ionized, as it rises, it's going to cool down, and electrons are going to start combining with the protons and change the amount of ionization, which will change the mean molecular weight, which translates into, that factors into the pressure that the bubble exerts, and it also factors into its temperature, because when electrons combine with ions, they give off energy and help keep the bubble warmer than it would have been if deionization, so to speak, were not occurring as the bubble rises. And so this will play a role in whether or not the bubble stays buoyant. Okay, so questions, comments, observations? Oh my God, I feel like it's like the last week of classes or something like that. Yes?
So for MH, the mass of the hydrogen atom, is that including the 13.6?
So it is, yeah. So the actual value of MH is, the actual value of MH, it's for the ground state. It's understood that the electron is in the ground state, the lowest energy configuration. MH is the mass of a proton plus the mass of an electron minus 13.6 electron volts divided by c squared. That's the actual mass of a hydrogen atom. And if you look up the mass of a proton and the mass of an electron and the mass of a hydrogen atom, you will see that the mass of a hydrogen atom is a little bit less than the sum of the masses of the proton and electron. And if you do the calculation, you will discover why it's actually 13.6 electron volts divided by c squared less. If you wanted to get it in kilograms, you could put those numbers in, turn EV to joules, divided by the speed of light, c squared. You would find the number of kilograms by which a hydrogen atom's mass is less than the mass of the proton and electron that combine to produce it. And that's true for any atom too. It gets more complicated though, because for helium, it's not just the binding energy of the electrons, it's also the binding energy of the nucleus. There's nuclear binding energy. That means that a helium nucleus has less than the mass of 2 protons plus 2 neutrons. It's that nuclear binding energy, and it's why the sun shines, because every time you build a helium nucleus out of 4 protons, the helium nucleus has less mass than the 4 protons did because of that binding energy that's been given up. That's the energy by which the sun shines. We'll get to that. That's the second half of this chapter when we talk about nuclear reactions and so forth. Okay? Okay, we still have a few more precious minutes here. Okay. So back to our story. Assuming mu does not change for the bubble or surroundings, which, as we just discussed, means no change in the amount of ionization. Because if you ionize, you're increasing the number of particles, and if you unionize, get those workers together, unionize them. Ha, 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 ha. It amuses me that unionize and unionize would be the same spelling, basically, right? So if you got, if your labor's been unionized, maybe it's been unionized. I get a charge out of it. Never mind. So no change in ionization level. Then I'll remind you that we did decide this is true because as the bubble rises, its pressure needs to stay the same as its surroundings, right? This has been a while, but this is true. This is true. This is not a condition. Always true. What's the argument there? Why is the bubble's pressure the same as the pressure of the surroundings? Put another way, what if they weren't? What if the bubble's pressure as it rose was higher than that of the surroundings? What would it do? It would rapidly expand to equalize the pressure, and vice versa. If the bubble's pressure were lower than the surroundings, it would get squashed. that will raise its pressure to make it equal to the surroundings. For a slowly rising bubble, that essentially means it just keeps up. The pressure in the bubble stays the same as the pressure in the surroundings. So this is true, the final pressures are true. And if it's going to be buoyant, it would be, we said that the final density of the bubble was less than the final density of the surroundings. These two things together with the ideal gas law what's the ideal gas law again in terms of the mean molecular weight and the density? Have you memorized it yet? It should become knee-jerk for you. The ideal gas law says P is rho something something over something something. Fill in the somethings. Right, rho KT over mu MH. Okay, look at what we got here. So in other words, if we say, okay, this could be pressure final, pressure of the surroundings, pressure of the bubble, they're the same, right? These are the same. So if the pressures are the same, but in the bubble, the density is smaller, what has to be true about the temperature in the bubble? It's got to be larger because they have to compensate for one another, right? Imply that the temperature, the final temperature of the bubble has to be greater than the final temperature of the surroundings for the bubble to be buoyant, and thus favor convection. Right, and if you didn't follow that, let's be a little more explicit, right? We know that the final pressure of the bubble is equal to the final pressure of the surroundings. So that says the final density of the bubble, K, times the final temperature of the bubble over mu MH is equal to the final density of the surroundings, K, final temperature of the surroundings over mu MH. And we're assuming that the mu isn't changing, that there's no change in the ionization state inside or outside the bubble. So these are the same. And K is K, right? So clearly, if the condition is that the bubble's density is lower, then its temperature has to be higher because the bubble's density times its temperature is the same as the surroundings density times the surroundings temperature. So if the density is lower, the temperature is higher in order to compensate and keep the pressure the same. That's the argument here. So that's our condition. The bubble has to stay warmer than its surroundings, and then it will float. Then it will want to keep rising. That'll be, and then we have to be a little more specific about that because the bubble is cooling down as it rises, but also the surroundings are getting cooler as well. And so what has to happen is the bubble has to cool more slowly than the surroundings do as it rises, so that it's always warmer than its surroundings. We'll be specific about that after the break. Go, run, no, drive, be musical. Blow bubbles into, I don't know, something.
I wish I would.
Upwards and upwards. Let's have a adiabatic expansion tour de force in a few minutes, but let's finish this thought that we're having here first. So the bubble has to stay warmer than its surroundings if it is to stay buoyant as it rises. And I've already said this in words, but let's put it, well, I'll say it in words again, but we'll put it down officially here. So Since dPdr is less than 0, right? In other words, the pressure drops as you get higher and higher in the star's atmosphere, and r is distance from the center. It's increasing upward. So since dPdr is less than 0, the pressure is lower higher up, then we know that the bubble expands, right? Because it's moving into a region where the pressure is lower than what it started with. We know that the bubble expands and does PV work on its surroundings as it rises. So in other words, the bubble cools as it rises, because when you do PV work, that's at the expense of the internal energy of the gas. And so it's going to drop its temperature. The bubble cools as it rises. So we know that's true. The bubble's going to get cooler because it's doing work by expanding against its surroundings. That cools a gas down. Classic example is, where it's extreme of this, is cold spray, quote unquote, right? Where you spray on your wrist. Oh, I injured my wrist. I want to make it cold. You spray something on it. Well, if you spray from a spray can, you'll notice that it gets cold, and that's because the gas that you're spraying out of is expanding rapidly and doing work on its surroundings and lowering its temperature as a result of that. So fun with physics. Okay, but since dTdr is less than 0, we know that the surroundings are also getting cooler as the bubble rises. It's finding itself in a cooler and cooler environment as it rises. We also know the surroundings are getting cooler as the bubble rises. In this case, it's not for the bubble, it's that particular gas that's getting cooler. For the surroundings, it's being surrounded by gas that is cooler than what it was surrounded with initially. But we'll just say that in terms of, we also know the surroundings are getting cooler as the bubble rises. So the bubble's getting cooler, the surroundings getting cooler. We want the bubble to stay hotter than the surroundings. In other words, we want the bubble to cool off slower than the surroundings do in order to stay hotter than they do. The surroundings have to cool off faster than the bubble does if the bubble is to stay hotter than they are. So our conclusion, our 3 dots conclusion is the bubble should cool less rapidly than its surroundings if convection is to occur. If it's to stay buoyant, and we've said that that's really going to be the condition that causes convection to set in. Because lots of bubbles starting to rise and continue to do so, and other bubbles sinking and continuing to do so, that's convection. So that's our condition. The bubble should cool down slower than the surroundings. Let's put that in terms of temperature gradients. But first, what questions do you have at this point? Okay. Thus, for convection to occur, we must have that, we'll do it in terms of absolute values here. It's easier to think of it in terms of taking absolute values. The adiabatic temperature gradient, in other words, how the rate at which the bubble cools with distance that it travels, dTdr adiabatic, should be greater than less than, because I actually meant to write this the other direction, less than dTdr actual. So in other words, on the right here we have how fast the temperature is actually changing in the surroundings with height, and on the left side is how fast the bubble's changing, temperature's changing with height. And so if the bubble's temperature change is smaller than the surroundings temperature change, if it's negative temperature change is smaller. So that's why I'm putting an absolute value there. If I took off the absolute value, I'd have to change this direction of the inequality, and then it gets really, starts to get confusing because wait, a bigger negative number is actually a smaller number. Oh God, so I just put it in terms of absolute values here. The bubble's adiabatic temperature gradient should be smaller than the surroundings. The bubble should change its temperature less than the surroundings do for it to be convective. So, does that make sense? What questions do you have? This is saying the bubble's rate of cooling is less than the surroundings rate of cooling. In words, that's what that's saying. The bubble's rate of cooling is less than the surroundings rate of cooling, so that the bubble stays warmer than the surroundings. They're both cooling down, but the bubble's cooling less. Flipping it around, because I accidentally put adiabatic and actual in that order. In my notes, I have it in the other order with a greater than sign. So flipping it around, the actual temperature gradient must be steeper in magnitude than the adiabatic temperature gradient. This is the kind of thing that you should be mulling over in your head later to be sure that you've got it down. It's the kind of thing that rewards some careful mulling over, because it can be the kind of thing is like, I got it. Oh, wait, what is that? Oh, no. Oh, yeah, I got it. Wait, what? Oh, yeah, I got it. And you want to get it to where it just is, I got it. So what's the dTdr for the surroundings? Well, to see if convection is going to occur, we're really choosing between, is it going to be radiative diffusion or is it going to be convection? So you can say, okay, well, what if I assume that the outside temperature gradient is the radiative temperature gradient? We have an expression for that. We wrote dTdr was something something when radiation transports the energy. So you say, okay, I compare the adiabatic temperature gradient to the radiative temperature gradient, and that'll tell me if actually convection is going to take over. So in practice, to to see if convection will occur. We calculate dTdr on the assumption of radiative energy transport. And if the magnitude of that radiative temperature gradient is greater than the magnitude of the adiabatic temperature gradient, so I'm just going to start shorting it to AD as opposed to adiabatic. If dTdr radiative, the assumed surrounding temperature gradient in magnitude, is greater than the adiabatic gradient, then convection occurs instead. Your assumption of radiative transport is wrong. It's convective transport. Convection occurs instead. In that situation, convection transports the energy more efficiently than radiative transport does. And so for the three of you and one at home, two at home, who are veterans of star spot research, I will point out that a strong vertical magnetic field suppresses convection in the sun's photosphere, where convection is the most efficient way to transport energy. You suppress convection, you force the transport to be via the less efficient radiative diffusion. And so inside the magnetic field of a spot where you've suppressed convection, now less efficient radiative transport takes over, which chokes off the flow of energy from below. There's still energy flowing into the spot, but it's occurring at the slower radiative transport rate instead of the convective transport rate. And so the spot cools down because less energy is flowing into it from below. And now you've got an equilibrium with the radiation it emits into space and the radiative transport into it from below, as opposed to the radiation that the surface is emitting in space and the convective transport below. Less energy flowing in radiatively means the spot has to cool down to balance the radiation from the spot into space with the transport by radiative diffusion into the spot from below. So additional perspective on all of that good stuff here. Okay? By the way, there's this really cool thing. Did you know that, I knew this before, but here's another example. The Mars Perseverance rover can photograph the sun, not in super high resolution, but it can. And if there's really large sunspots, it can see them. And there's a really big sunspot group coming around, visible to us on the sun right now, which the Perseverance rover spotted a few days ago when it was on the far side of the sun viewing it from Mars, which I think is pretty freaking cool, as a matter of fact. And they're spots, so of course they're cool. Anyway, I never get tired of that joke. I know, it's just always fresh and hilarious. Yes. Okay, so it can be shown. It can be shown, so of course now we need to wave those chicken feet. It can be shown that when convection takes over, the resulting actual temperature gradient is only slightly super adiabatic That's the fancy word for exceeding the adiabatic gradient. If the surroundings gradient is steeper than the adiabatic gradient, then that's when you don't, that's when you will get convection, so you need a super adiabatic temperature gradient. And that it's just begging for there to be a song, right? Because it's like, you know, as opposed to supercalifragilisticexpialidocious. I want to be like super adiabatic transport, something. I don't know, work on that. Super adiabatic. So to a first approximation, which we will indeed make, to a first approximation, we can set the temperature gradient to the adiabatic value. And so, with a few pages of work, we're about to deduce what is the adiabatic temperature gradient. This is going to be so much fun. We're going to be like ideal gas lowing the heck out of everything. A different word came to mind, but in any case, let's do this. All right, so the adiabatic temperature gradient. All right, so this is a few fun pages worth. We'll get there. It's a few fun pages worth. So AKA Moby Dick, the adiabatic temperature gradient. But this is good stuff, because this is good practice thinking about thermodynamics and stuff like that. So, first law of thermodynamics. So I think you all met this in 111, is that true? You did some thermodynamics, is that right? Some, yeah, okay. And then have you, I forget, have you had or not had StatMech yet? What's that? Did or did not? Did not, okay. Good, this is practice for that. This will be like, you know, I mean, we won't be doing statistical mechanics, but you'll be reminded of regular old classical thermodynamics kind of stuff here. So, du is dq minus dw, and sometimes we put little slashes on these differentials to say they're actually not differentials. It depends on the path that the system takes. I'm not going to bother with that. Whereas du is an actual genuine differential. It's a state variable. It's something that is a property of the fluid independent of how it got that way. So du equals internal energy of our fluid. dW is dQ is the heat flow into the fluid. So if heat flows out of the fluid, dQ would be negative, in other words. And dW is the work done by the fluid on its surroundings. So into the fluid from the surroundings. And dW is the work done by, that's important, it's the work done by the fluid on its surroundings. That's a choice. We could have made it plus dW if we wanted to make it the work done on the fluid by the surroundings, but we're doing by the fluid on its surroundings. Right? So the idea is you can change the internal energy of the fluid, which is really, in other words, the internal thermal energy. I should say it's like this internal thermal energy. Right? So if it's an ideal gas and you ignore potential energy interactions between the particles, it's just the sum of the kinetic energies of the particles, the thermal kinetic energies. If it's not an ideal gas, you have to account for the fact that, yeah, but they're also interacting with one another with electrostatics and stuff like that. But if it's an ideal gas, it's just the total kinetic energy, thermal kinetic energy of all the particles. So this is saying that if heat flows in, why, that increases the internal energy. But if the fluid does work on its surroundings, that's at the expense of its internal energy. In other words, this is energy conservation is what this is saying, okay? So does that make sense? What questions do you have? Have you seen this before? Did you see this like in 111? Is that true or not true? Who knows is your response. Maybe, right. You did, I'm sure you did. Now, you might have used different notation, but dq and dw are pretty standard. du, not everybody uses du, but I am. Deal with it, because your book does. Deal with it, okay? So, we will use these quantities expressed per unit mass. So in other words, implicitly, we're kind of always dividing by the total mass of the fluid. So du is not the energy itself, it's the energy per unit mass. Energy that flows, that's the total energy of the fluid divided by its total mass. dq is not the heat flow itself, it's the heat flow divided by the mass of the fluid. Same thing for dw, we're always dividing through by the mass of the fluid. All right, so now we do the classic, let's consider some gas that is trapped behind a piston. So here's a piston. Here's the piston right there. I'll put a dashed line. So it's a cylindrical piston, and we have right? This is the chamber, here's the piston, it's got a plunger attached to it. I can push down on the piston, and there's fluid trapped by the walls and the bottom of the cylinder, and the plunger, if you will, of the piston. So if I push down on it, I'll be doing work on that fluid. And if I let go and the fluid expands, it'll be doing work on its surroundings. And we say, okay, suppose that the fluid is displaced some distance dr, and let's suppose it's upwards. I'm saying dr because we're in the star, and the center of the star is down there somewhere, and so we have the fluid there is expanding, pushing the piston upwards, if you will. We don't have pistons in stars, but we still have fluid elements that are expanding against their surroundings. Same idea. So, piston moves up a distance dr. So the work that the trapped fluid does on the surroundings will be equal to force times displacement, right? Force times displacement. dW is FdR, force times displacement. dW is Franklin Delano Roosevelt, force times displacement. You're like, wow, I guess FDR did a lot of work. All right, so, okay, let's see. Now, the force in terms of the pressure and the area of the piston there, what's that? Force in terms of pressure and area, what's that? Force is blah, blah, blah in terms of pressure and area. What's pressure?
Pressure times area.
Yeah, pressure times area, right? Because pressure is force per unit area. So this is going to be pressure times area times dr, but we're doing it per unit mass. So remember, everything is per unit mass, which is why I'm dividing by m. I don't have to do that. We could do this without doing that, but we're doing everything per unit mass. So we divide by m because it's per unit mass. But wait a minute. What is A times dr? So has the volume of that trapped fluid changed as the piston moved up? Well, it did, right? I'm expanding it, right? It's expanded, so that it's occupying more volume. Yes, question? Yeah, so how much more volume? dV, right. AdR is dV. dV, change in volume. So we can say that this is P dV, where, well, I'll put it this way, I'll be a little more close. So this is P d volume. So let me say, yeah, okay. This is the change in volume, because I'm going to use V for a different, I'm going to use V to mean volume per unit mass, because everything's per unit mass. So it's PD volume over M, or in other words, it's PdV, where V equals 1 over rho is the volume per unit mass, because everything is per unit mass. So in other words, I don't want to call, I'm using the symbol V, which we normally use to mean volume, I'm changing it to mean volume per unit mass. And this is making Kathleen sad, but it's okay, because she will get used to it. She too will learn to love everything per unit mass here. Where V equals 1 over rho is the volume per unit mass. Also known as the specific volume. Right? In other words, rho is mass per unit volume. 1 over rho is volume per unit mass. So this is the differential of 1 over rho, which we're calling the differential of V, where V is the volume per unit mass, the reciprocal of the density. So du is PdV, which means du is dq minus p dv. And again, you can do this not per unit mass and just talk about that we got a certain amount of fluid, but we're dividing through by the mass of the fluid. du is dq minus p dv. And this is super important. Right? So the PdV there, that's the pressure volume work. That's the PV work that the gas is doing on its surroundings. As our bubble rises, it's doing PV work on its surroundings by increasing its volume. And you've probably seen that. Is that true? Did you do this in 111? Probably. I feel like you sort of remember, but not sure, or something like that.
It looks familiar.
It looks familiar, okay. Well, good, because reinforcement is the key to learning. So let's reinforce, shall we? All right. The internal energy per unit mass is U equals, put it over here, U equals the average energy per particle times the number of particles per unit mass. Right, because we want is the energy per unit mass. And so if we take how much energy there is per particle times the number of particles, then that would give us the total amount of energy. And now if we put it in, we want per unit mass, we can do average energy per particle times number of particles per unit mass will give us the energy per unit mass. The average energy per particle, if it's an ideal gas and it's all kinetic energy, and it is monatomic, you may recall, we've mentioned before, and this is another, take my word for it, and when you take stat mech, you'll see where this comes from, 3/2 kT. Remember we were talking about the Maxwell-Boltzmann distribution. VRMS squared was 3 kT, and so therefore over m, I guess it was, so then 1/2 mVRMS squared was 3/2 kT. So the average kinetic energy per particle is 3/2 kT from the so-called equipartition theorem times, and for the number of particles per unit mass, well, that is going to be 1 over mu mh, because remember that mu mh is the mass per particle, average mass per particle. So its reciprocal is particles per unit mass. Too low. So U is 3 kT over 2 mu mh. But this in turn is 3/2 ny RT, n tilde RT, which I can't help saying ny for. 3/2 n tilde RT. So now we're going to get all like chemical or something. We're going to use moles. Holy moly, we're switching to moles here. I can hear the celebration building behind me. Yes, there it is. Where n tilde is equal to the number of moles per unit mass and R equals Avogadro's number times the Boltzmann constant equals 8.31 joules per mole per Kelvin is the beloved gas constant, right? The PV is nRT, it's that R, is the gas constant. How did we get this? I'll show you in a second why those two things are equal to one another. this follows from Avogadro's number is, in fact, 1 over n tilde mu mh equals, so n tilde is moles per unit mass, or in other words, SI would be moles per kilogram. So this is going to be 1 over n tilde is kilograms per mole, number of kilograms per mole, and then we're going to multiply that times the number of particles per kilogram, right? Because 1 over mu mh, we argued, since mu mh is kilograms per particle, its reciprocal is particles per kilogram. So number of particles per kilogram. So that's true. So 1 over n tilde mu mh is that combo right there. So that says that n tilde r is equal to n tilde times Avogadro's number times k is n tilde times 1 over n tilde mu mh times k equals k over mu mh. So k over mu mh over here is indeed n tilde r, and so I can make that replacement. What questions do you have? That's another thing that's worth reviewing with yourself later to be sure that you see all the logic in that, because it's easy to kind of like, wait, what? Get lost. So stare at it a little bit and be like, drill that into your head. Now, if it wasn't already fantastic that we're going to be dealing with moles per unit mass, buckle your seatbelts, because we're also going to talk about the ratio of specific heats. Right? Remember that business, like CP over CV and all that kind of stuff? This is definitely showing up here. So, adiabatic processes involve the ratio of specific heats. Involve the ratio of specific heats at constant pressure and constant volume. So that is gamma. There's not enough symbols to go around. That's not the relativity gamma. This is a different gamma. Gamma is Cp over Cv. Cp is the specific heat at constant pressure. Cv is the specific heat at constant volume. And remember that the specific heat is the amount of energy that it takes to raise the temperature by 1 Kelvin. Right? Remember that? It's the specific heat is the amount of energy it takes to raise the temperature by 1 Kelvin. You say 1 Celsius, but how does a Celsius compare to a Kelvin? How does a Kelvin compare to 1 Celsius degree? They're the same temperature interval, right? So the specific heat is how much energy it takes to raise the temperature by 1 Kelvin. Right? So different substances have different specific heats because it takes different amounts of energy to raise the temperature of different substances by 1 Kelvin. So the specific heat at constant volume is dq over dt at constant volume. That's what that symbol means. It's the ratio of heat flow in divided by temperature change at constant volume. The means at constant volume. Right? So in other words, if the temperature change was 1 Kelvin, then dq would be equal to that heat that you need to produce that. So CV in general is the ratio of how much heat you put in divided by the temperature change. But from our earlier expression, right, we said that du is dq minus PdV. Turn that around, dq is du plus PdV. So this is du dt at constant volume plus P dV dt, and volume depends on more than temperature, so we're calling it a partial derivative at constant volume. So I've replaced dq with du plus pdv, and these manipulations may not be familiar to you. They will become familiar because we're doing them here, this kind of logic here. But wait a minute. What is the rate of volume with respect to temperature if you're holding your fluid at constant volume? How much is the volume changing if you're holding the fluid at constant volume? This is 0 by definition in this case. Equals 0 by definition. Right, and I'll remind you, because maybe you've forgotten this idea, is, okay, here's our piston, okay, and here's our trapped fluid, and doesn't have to be this, but it could be like flames. We're heating up that trapped fluid and seeing how much its temperature rises, and taking how much heat it absorbed and dividing it by how much the temperature changed. That is the specific heat at constant volume. How do I make this stay at constant volume? What has to be true about that piston if this is to be done at constant volume? Can the piston move? No. So you have to lock the piston in place. You don't allow the piston to move, so that all the heat flowing in goes into increasing the temperature of the fluid. But if you do it at constant pressure, you release the piston, and in that case, it maintains pressure equilibrium with surroundings. Here it doesn't. If I lock the piston in place, there's no reason it has to stay the same pressure as the surroundings. It has a constant volume. But if I release the piston, it will rise, always keeping the pressure the same as the surroundings, because otherwise it would expand or contract to equalize the pressure. So here we're doing it in the constant volume case. Well, the rate of change of volume with respect to that increase in temperature at constant volume is 0 by definition. We're not letting the volume change. And so for the constant volume specific heat, it is the derivative of U with respect to temperature at constant volume. But here's the thing, U doesn't care. The internal energy is 3/2 n tilde RT no matter what. The internal energy, all it cares about is how fast them particles moving, what's their average kinetic energy. And so constant volume, constant pressure, U is 3/2 n RT no matter what, 3/2 n tilde RT no matter what. So this is derivative with respect to temperature of 3/2 n tilde RT. This is U, period. Doesn't matter whether constant pressure, constant volume, or somewhere in between, that's the internal energy for the ideal gas. It's just the kinetic energy of the particles, and it only depends on the temperature in terms of, and an R, but in other words, it doesn't depend explicitly on volume or anything else, it's just temperature. So, quick, what's the derivative of 3/2 n tilde RT with respect to T? Yeah, 3/2 n tilde R. So what have we decided? The specific heat at constant volume is 3/2 n tilde R. And again, this is per unit mass, right? This is the energy per kilogram put in to change the temperature by 1 Kelvin. What are our assumptions here? It's a monatomic ideal gas. That's what made it 3/2 nRT. Monatomic ideal gas, which is often what we're interested in. Monatomic ideal gas. And also we're assuming constant value for n tilde, the number of moles per kilogram. What could change the number of moles of particles per kilogram? Put another way, what could change the number of particles per kilogram in that gas as I'm heating it? What could happen that could increase the number of moles per kilogram? Because here the moles, we're talking about moles of any type of particle. Every particle counts in the ideal gas law. Doesn't matter what kind of particle it is. Every particle, a particle's a particle in the ideal gas law, as long as it's acting as a cohesive unit. So in other words, an atom with an electron bound to it, that's one cohesive unit because they move together at all times. That's one particle. I'm kind of hinting, what could change n tilde? Yes? Ionization, yeah. So the constant n tilde is not just an empty assumption, it's not automatic. It could become ionized as we heat it up, and that would change this result. The specific heat is higher if you allow ionization because some of the energy is going into ionization instead of heating up the gas in that case. Similar to the way, so you bring water to a boil. At sea level, it boils at 100 Celsius, okay? You got the flame on there, it's boiling. Does the temperature of that water change if you turn up the flame? Not sure if you've, right? It doesn't, right? Because when water is boiling, all the energy goes into the phase transition, goes into changing water to the vapor form, right? So if you don't know that, now you do. And if you forgot that, remember it again. When a substance is undergoing a phase transition like that, like boiling, all the energy is going into that phase transition. Now, ionization is different because it's not sudden, right? So it's a different type of phase transition. If you have a phase transition like water boiling, that occurs at a constant temperature. To heat water above 100 Celsius at sea level, you have to vaporize it, and then you can make the steam get hotter than 100 Celsius. But while it's boiling, it's holding steady at 100 Celsius. Similarly, if you have a chunk of ice surrounded by water, you got that, you're making that phase transition of freezing. It's staying at 0 Celsius the whole time. As long as there's got ice water there, if you heat it, well, you're not changing its temperature, you're just melting ice instead. It's all going into the phase transition. Ionization isn't that kind of phase transition because it's gradual. There's not a temperature where it suddenly goes from ionized to not ionized and vice versa. So it's not a gradual phase transition like that. But nevertheless, in this case, you can be putting in energy, and if it's ionizing, you're reducing the rate at which the temperature is rising because some of the energy is increasing the amount of ionization. As opposed to when you're boiling water, as long as there's still water there and it's boiling, you can't raise the temperature. It's just going into the phase transition. So it's a bit different here. But anyway, yeah, time to go. 5 free minutes of education. You're welcome. I know, don't thank me now.